Marino's Quantum Optics group at the University of Oklahoma. My talk is going to be the latest progress we had to apply the quantum states of light to a real-life measurement to enhance the sensitivity because of the squeeze states property and their noise reduction property. This work has been collaborated with Oak Ridge National Lab, and I should acknowledge the support from the Keck Foundation. As you all know, if you're using a classical states of light to probe and use a probing beam to a classical measurement, the sensitivity is basically limited with the shot noise limit. And if you want to surpass that limit, you have to use quantum states or quantum squeeze states of light, which is in our case bright two-mode squeeze state. One of the good candidates that can be benefited from these states are plasmonic sensors, which are biomedical sensing devices, very widely used, and they have already reached the shot noise limit, and they are also compatible with the quantum resources. It means that if you're probing these states, these sensors with the squeeze states, entanglement properties will maintain and they're not destroyed. These sensors are index refraction sensors, and they can, as they're probed with the light, they can modify the phase or the amplitude of the beam or transmission of the beam. Therefore, we can probe them by monitoring changes in index refraction, by monitoring transmission changes or phase changes. Here, we're going to compare how much we can enhance or how much we can benefit from quantum properties from a measurement scheme based on transmission and phase. In order to have an absolute and fair comparison between these two protocols, we're going to go to the measurements which can saturate the quantum parameter raw bound, basically. So we're going to compare these sensitivities at the bound and with equal resources. To implement such a quantum enhancement of sensing, we need three ingredients. One is, of course, the source. As I said, it's going to be a four-mixing process generating bright two-mode squeeze states. We need the sensor itself, by which we're monitoring changes in transmission or phase, which is introduced by the sensor. And we need a compatible and proper detection scheme in order to detect changes, whatever we want, transmission or phase. First of all, I'm going to talk about the source of our light in our lab, which is the four-mixing process in D1 lines of rubidium-85 atoms. The whole process happens in a double-launcher configuration. As you can see here, two pump photons will be absorbed, and they allow simultaneous generation of pairs of photons with frequency of probe and conjugate. These two beams they show quantum properties. If we send them to a photodetector, subtract the signal, we will see the noise will be reduced below the shot noise. Then can be generated with a coherent state, randomly generated photons reaching to the detector. Here we're going to talk about the temporal properties of the light. My colleague Awin will, in the next talk, is going to talk about temporal and spatial properties, which is basically the sourceless quantum lights in our lab. So we're using the probe of the twin beams for probing the plasmonic sensor and use the conjugate beam as the reference beam. But the plasmonic sensor itself is composed of a nano layer of silver, which has nanovolt structures in it, and an array of nanovolt structure. And as it's illuminated with light, excitations of electron at the interface of metal dielectric can be coupled at the two interfaces, and they can talk together, they can be coupled in resonance, and the light can be transduced from one surface to the other surface extraordinarily, which cannot be explained with the diffraction theory. That's why it's called extraordinary optical transmission, EOT, and in theory it has a Lorentzian distribution from which we can directly get the transmission and phase information out of it. This is a sensor of index refraction because if the index refraction around this structure changes, the whole transmission and phase change or shift basically to longer wavelengths, and we're probing it with single wavelength source. Then changes in index refraction can be monitored by changes in transmission and phase. The sensitivity is basically the inverse of the minimum resolvable changes that we can detect, delta and min. And it directly, delta and min directly relates to the smallest value of, the smallest invariance of transmission and phase, and also inversely proportional to the slopes of transmission. So If we have sharper slopes, we have more sensitivity. The quantum Cram Raman that I just mentioned earlier sets the lower bound on the variance we can estimate here. So as I said, so we have a source of our squeeze states, we have a sensor, and we need a detection scheme based on transmission and or phase. Here is a demonstration for transmission-based sensitivity measure enhancement with squeeze states, which is basically composed of two photodetectors and subtracting the signal with an electronic attenuation for the conjugate to compensate losses introduced by the plasmonic sensor. Our colleague in our lab, Timothy Woodworth, has shown that this set of measurement can saturate the quantum Cram for any value of transmission, and this is basically the variance for delta T min. We have done this experiment last year and showed that, which results are published in this paper over here. We have shown that with starting with 9 dB of squeezing, because of the losses through the plasmonic sensor, we're ending up with 4 dB of squeezing, but we can have, with the remaining 4 dB of squeezing, we can have 60% enhancement, resulting signal from noise with the twin beam compared to the resulting signal from noise with the coherent state. Excuse me, that was a loud noise. Sorry about that. So on the other hand, if we want to have a phase-based scheme, so we need to have two phase-sensitive measurements for the probe and conjugate, which is of modern detections for probe and conjugate. From Professor Lett's group, people have shown, this is one of the papers that they have shown, that this scheme can saturate the quantum Cram when there's no optical losses introduced in this setup. It means that if transmission of the plasmonic sensor is 100% ideal EOT process, we can saturate the bound. But with different values of transmission, we can still have an upper limit for this quantum Cram bound. So here we're going to compare the variance in phase versus variance in transmission for different values of transmission and for different levels of squeezing, but keeping in mind that we're going to compare them with the same amount of number of photons censoring or reaching the sensor. The results are plotted here. So we see that with a phase-based measurement, we have the minimum value over here, which is corresponding to the maximum transmission on this transmission spectrum. And at this point, we have the slope is 0. Basically, we don't have any sensitivity for the transmission-based measurement, which is in the denominator. So we see that the delta n with transmission blows up to infinity. So it means that it's not a good point to operate the plasmonic sensing at the peak of transmission. So it means that intrinsically, plasmonic sensing at the peak with the transmission-based information or measurement is going to be off the peak, introducing some noise by itself. But with a phase-based measurement, we can see that the phase at the peak of transmission, but it still have the maximum transmission sensitivity. This is a comparison with the coherent state. On the other hand, if we use the squeezing source, we will see both transmission and phase-based sensitivities will be benefited, but it's still phase-based measurement shows better sensitivity. In order to get an idea of how much phase-based measurement is better to compare to transmission-based measurement, so we go and take the ratio between the minimum value here divided the minimum value with transmission for different levels of squeezing, for different levels of basically maximum peak of transmission, this Laurentian here. This ratio, we call it figure of merit. It shows that how much phase-based measurement are better. We see that even with no squeezing, basically with the coherent state of light, phase-based measurement shows at least twice better sensitivity in the sensitivity, and that is because the slope is shorter, right? And if you're comparing them at the case of no losses introduced, which is the quantum Cram bound, we see that the phase-based measurement can reach up to 4.5 times or even more when we have 10 dB of squeezing in our resources. On the other hand, if you see that with the extreme case of introducing 90% losses in our system, we still can benefit from the phase-based measurement, but 10 dB squeezing is acting like coherent state. We cannot get anything from quantum properties. So to summary, I have to say that, so we have implemented quantum measurement or quantum enhancement of the plasmonic sensing, and we have compared the sensitivity of the two modes of measurement with plasmonic sensing at the quantum parameter raw bound. We have shown that phase-based setups are at least twice as sensitive as transmission-based setups, and that is because of the two factors. One, they have sharper slopes. The other one, they are happening at the peak of transmission spectrum, so they are not introducing any loss because of the mechanism of measurement. And the last part, in the future steps of our research, we're trying to design and simulate the plasmonic structures to introduce the least amount of losses and also the sharpest slope possible. Thank you.
And we have time for one question while the next speaker sets up. I'll ask a question. Sure. What's the limit to the amount of light you can send in the plasmonic sensor? Because, you know, in what situation would it be better off to squeeze than just to send in more light?
Right. I mean, in all of these comparisons, you're talking about the same number of photons to be fair, but that's true. We can send more light, more sensitivity, but the plasmonic sensor has some threshold of not to fly, or the detectors have some sensitivity limits, basically. Those are the two limits.